magnet at that, and it has no effect on this whatsoever. None. Yeah. You know, it'd be curious, and we could probably find this out very easily, what superconducting magnets, whether they're superconducting at room temperature.
I mean, the more you look at it.
John just, yeah, you know, I kind of thought these were the same, but he's right, it's not. This, we should get something to clean this. Have you tried cleaning this with any solvents? Okay.
No.
Well,
I didn't want to.
It's difficult. Yeah, it's difficult. Well, I don't think you're going to pollute it. This has a reflection to it. It looks like.
Oh yeah, and I can see it in the camera. It's got a sheen.
Yeah, and this
it's
is
unbelievable.
This is, like you said, I believe this is a ceramic, and this is a metal.
It is. It's, so you've got three composites here.
Yeah. Huh. Because, you know, it makes sense if these were stacked somehow, that this metal would be conducting through both sides from one to the other, and that the ceramic coating could be some kind of insulator.
Wherever you find ceramic,
it's an insulation.
You find it as either protection against high heat, primarily, or something that's extremely strong and will maintain.
Yeah, I'll tell you what, I was a little bit skeptical, John, but I'm beginning to see why you think this is really, really something.
Yeah,
because it is. This is not the same material as that. There's no question.
Yeah, you've got three separate composites: one metal, one ceramic, and the other one you have to be identified in the middle.
Right.
Which to you looks like, you know, the center of a magnet.
You know, I'll tell you what.
It has no magnetic.
Let me try something. I've got a infrared. I got a special tool that I use for infrared emissivity.
Oh, really?
Yeah, it's like $600.
Okay. Can I go down and get my cigarette?
No, you can't.
The temperature difference between the rock and that, I guarantee you.
Well, watch this. So the camera can see it. Try that. This is a the tool that we're going to use is a Fluke 68 infrared thermometer. Its setting is at let's see, let's get this up, 0.95 emissivity, and let's see if we can get that. That's 81.9 degrees on the black surface, and when we come down to this other surface, it drops to 79.
And then when you hit the ceramic surface, it drops to 77. It's got three different temperatures on one piece of material.
Yeah, there's no
this is cool. This shit is cool.
There's no question. Now, when we look at it again in the middle, though, we're at 78. We come up to the top metallic, it goes up to 81.
And then your ceramic.
Yeah, go ahead and turn to the ceramic side.
There you go. You can get all three of them that way.
Yep. And 75 degrees.
And what's that? Take it in between the two.
And I don't
look at that. 80.
Yeah.
80, 70, and it's right in between the two. So you've got a 4 degree, 5 degree. Look at that. That's amazing. See, that's a function of a component. It's reactive. It's reactive in three different dimensions, three different temperature gradients.
Well, I think you hit the nail on the head. I think that these were coupled, and that this is the conductive surface, the metal surface, and that just like you said, I mean, I think you put a lot of thought into this.
Well, I've had a couple of years of thinking, and I think this was the original arrangement of what it came from.
This is John's drawing.
What I consider to be the original arrangement of it because of the geometry. If you put this in the middle and then draw more of these around, you'll end up with this picture here. These are transposable into any quadrant that you want to use it. And there's the other piece there. And if you had the rest of them, you would have a composite.
And so possibly there was multiple.
And well,